Hello friends, welcome to my YouTube channel. After a long time, I am back with some hardcore mathematics. In this video, I am going to talk about infinitude of primes from a topological viewpoint. We all know what is a prime number, but for the sake of completeness, let us define it here. An integer p greater than or equal to 2 is said to be a prime number if it has no proper divisor. That is, 1 and p are the only positive divisors of p. It is well known that there are infinitely many prime numbers. There is fairly a long list of independent proofs of the fact that there are infinitely many primes using different viewpoints, starting with the most popular and perhaps the most ancient one, which is usually attributed to Euclid. However, all these proofs have one common thread. All of them rely on the following fact. And the fact is, every integer other than plus or minus 1 is divisible by a prime. The basic idea behind Euclid's proof is as follows. Given any finite set of prime numbers, the existence of a prime divisor of the number 1 plus product of the members of finite set of prime numbers guarantees the existence of a prime number outside the set P. So this particular number is different from plus or minus 1, and by that common fact, this particular number is divisible by a prime, and that prime divisor cannot be one of these pi's, otherwise it will divide 1. Hence, any prime divisor of this must be outside this p. So this in turn proves that the number of primes cannot be finite. Okay. In this video, we discuss a proof of the infinitude of primes from a topological viewpoint, which was originally proposed by Harry Furstenberg, a German-born American-Israeli mathematician. Okay. Let us recall some basic things from topology. Given a set X, a family Tx of subsets of X is said to be a topology on X if empty set and the whole of X belongs to that family Tx. Tx is closed under arbitrary unions and Tx is closed under finite intersections. Okay. A subset U of X is said to be open in X if U is a member of Tx. And a subset V of X is said to be closed in X if its complement is a member of Tx. Like this. So if its complement is open, then the set is called closed. So now we start the proof. That means topological proof of the fact that there are infinitely primes. We begin by defining an interesting topology Tz on the set Z of integers. Although Tz is different from the one induced by the usual topology on R, yet the underlying idea remains the same. For two integers a and r with r positive, let us consider a set n suffix ar which consists of all numbers of the form a plus a multiple of r integral multiple of R. So, okay. Note that each NAR is a two-way infinite arithmetic progression. More precisely, NAR looks like this. So, start with A and keep on adding multiples of R. So, A plus R, A plus twice R, and keep on subtracting multiples of R. So, A minus R, A minus 2R, A minus 3R, and so on. Okay. So, this is the structure of NAR. An interesting observation is as follows. If you have three integers A, R1, R2, where R1 and R2 are positive, then NA, R1 into R2 is contained in the intersection of NAR1 and NAR2. That is because any multiple of R1 and R2, any multiple of R1 into R2 is also a multiple of R1 and is also a multiple of R2. Therefore, every element of this set is here as well as here. In what follows, each NAR is going to act like a neighborhood of A having radius R. That means it is, if you consider real line, NAR is going to act like the open interval A minus R, comma A plus R. So let's see how it happens. We now define the members of TZ. So the topology TZ which we have talked about earlier, we are going to define it now. So we are going to tell you exactly which subsets of Z are here in TZ. So basically we are going to talk about open subsets of Z under this. So let's see. We proceed by adopting exactly the same method by which one defines the open subsets of the real numbers. Given a subset U of Z, let us write U belongs to TZ, that is, let us call U open in Z if the following condition holds. What is that? The condition is either U is empty or for every A, U contains a neighborhood of A. That means U contains some NAR. Clearly, we have empty set and the whole of Z as members of TZ, right? Empty is obviously by definition, and Z, after all the neighborhoods are inside Z only. So that is why entire Z is in TZ. It is equally easy to see that the union of open sets in Z is open in Z. Okay. That is, if this is a arbitrary family of members of TZ, then their union is also a member of TZ. Because each EY contains a neighborhood. Okay. You choose any point in the union, that point will be inside one of the, at least one of the U alphas, and U alpha being open, there is a neighborhood inside U alpha containing that particular point, and that neighborhood is contained in here also. Now we consider two sets U1 and U2 in TZ. So both are open in Z, and let A be a point in the intersection. Now A is a point in U1, A is also a point in U2, and both U1 and U2 are in TZ. So there is a neighborhood of A inside U1, there is a neighborhood of A inside U2. So these are the neighborhoods NAR1 and NAR2. So by that interesting observation, NAR1, R2 is contained in the intersection of these two neighborhoods, and these two neighborhoods again now will be contained in U1 intersection U2. So if you start with a point A in the intersection, in this way you can produce a neighborhood of A inside this intersection. Thus it follows that TZ is indeed a topology on Z. Note that in the topological space Z Tz, the following assertions hold. What are they? First one is every non-empty open set in Z is infinite. That is obvious because since non-empty, so there is a point, and since there is a point in that set, and since open, there is a neighborhood containing that point inside this set, this inside this open set, and neighborhoods are infinite sets. Okay, and therefore these open sets are infinite. And the second one is each NAR is a closed set. By definition, it is easy to say that each NAR is a open set because NAR itself is a neighborhood. So it obviously contains a neighborhood, namely itself. So it is open. But this assertion says that it is not only open, it is also a closed set. First one, as I have already mentioned, follows immediately from the definition. And for the second one is to see exactly which points do not belong to this neighborhood NAR. NAR consists of these points, A plus multiples of R. So which points do not belong to this set? The points which do not belong to this set are precisely this type of points, A plus NR plus 1, A plus NR plus 2, up to A plus NR plus R minus 1. The next point is NR plus R, which is same as N plus 1R. So that one belongs. Okay. So simply look at the numbers between between A plus NR and A plus N plus 1R. All the numbers between this, excluding these two numbers, actually belong to the complement of NAR. They lie outside NAR. So this set is outside this set, and so these R minus 1 sets actually constitute the complement of NAR, and this set is obviously same as NA plus 1R. Okay, whether you write a plus 1 here, this plus 2 also here, then it is exactly this one only. So thus it follows that the complement of NAR is precisely equal to the union of NA plus I comma R, where I runs between 1 and R minus 1. So it is greater than 0 at the same time less than R. And it is clearly an open set because it's a union of open set. These neighborhoods are open. Okay. Recall that every integer n different from plus minus 1 has a prime divisor p. We have already mentioned this fact. And so this particular neighborhood, which is of n obviously belongs to this neighborhood. So this particular neighborhood, since every n is a multiple of p, some p, so this particular neighborhood is contained in n0p, this neighborhood. Okay. Okay, any multiple of n is also a multiple of p. So this is contained in this. So for every n, we have some p. So therefore, it follows that if you all the numbers different from plus minus 1 are actually inside this union, where p runs through the set of all primes. Okay, small p runs through the set of all primes. And right hand side, of course, is contained in the left hand side, because this side, although they are all integers, but 1 and 1 do not belong here, because p doesn't divide 1, p doesn't divide minus 1. Okay, so 1 cannot belong to n0 comma p. 1 is not a multiple of p. 1 cannot be written as 0 plus multiple of p. Okay. If p were a finite set, then this union would be a finite union of neighborhoods. But these neighborhoods, we have seen according to the second assertion, these neighborhoods are closed. So this will become a finite union of closed sets. Hence it will become a closed set. So that means this particular object, this particular complement becomes a closed set, which means this set plus minus 1 becomes an open set. All right. So consequently, this would become a open set. But again, this is a contradiction because according to the first assertion, every open set is infinite. But this is a finite open set. So this contradiction shows that our set of primes cannot be a finite set. Okay. So that completes the proof. Hope you have enjoyed the video, and this video will be useful for you in your seminar or anywhere. If you would like to present, you can do so. So that's all in this video. Thanks for watching.